Now, in my last video, I showed that flat earthers are actually contradicting themselves. Now, on one hand, they are making the claim that sextants only work on a flat earth, and this is because of right triangles. But at the same time, it was argued on this recent show on Brandon's, any calculations made with those right triangles are incorrect. Of course, the main line of attack was that these calculations do not account for perspective, which is absolutely hilarious, because when we're dealing with perspective or the apparent size of objects, we are talking about their angular size, and we use trigonometry to make angular size calculations. Of course, their complete misunderstanding of how perspective really works was why a glober finally coined the term Flerfraction. Now, there's a newer flat earth belief that any of these observation discrepancies can be solved with refraction. So, of course, this was another question that they posed, and that is going to be the subject of this video. Now, when I get done with this, I think you might agree with me that we need to coin a new term, Flerfraction. So yes, atmospheric refraction is real and corrections are made for it in celestial navigation. So let's start off by taking a look at this calculated angle of 26.7 degrees at the equator on a flat Earth for Polaris. So here is where Polaris should be observed on a flat Earth. So all we need to do is just add refraction and look, it works. Let's have a little fun and compare what we actually see from the equator to the 40th latitude and compare that to what we should see if the Earth was flat. So these are the angles where we would expect to see Polaris above the horizon. These are the calculated angles for Polaris on a flat Earth, and the yellow is how much refraction would be required to bring Polaris down to where we would expect to see it. Now at 40 degrees, this is a difference of 2.2 degrees. And for a frame of reference, that would be the equivalent of about 4 suns stacked on top of each other. Now I want to compare this to what we saw in the Black Swan photograph because we actually asked flat earthers the exact same question. Now this is from the original video from BML SB69, and he actually said that on most days this is what he saw. So I did some research. All of these platforms have a heliport on them, and on Platform Hill House, that heliport is about 98 feet above the surface of the water. Now at a distance of 6.2 miles, this is how big it is in angular size, 0.18 degrees. And here's the Black Swan photo, and again the heliport is about 0.18 degrees in angular size above the surface of the water. Now it's not a very clear photograph, but it does appear that we see a horizon back here, but that means that it was loomed up only 0.02 degrees in angular size. Now a person that has 20/20 eye vision has a resolution of 0.0167 degrees, and that is just a little bit smaller than how much that horizon was loomed up. Now of course this photograph was magnified with a P900, but 0.02 degrees in angular size would be smaller than a period at the end of a sentence in a book. And what happened when we asked the flat earth community if they considered refraction? Well, they were adamant that this was absolutely impossible. And that was in spite of evidence of a similar refractive phenomena in this photograph called towering. Now I used these dotted arrows right here so I could take this normal photograph of this platform and make sure that the width was the same as it was in the Black Swan photograph. So the bottom yellow line shows that the bottom deck of both platforms is in alignment, and the top yellow line shows where the heliport should be over here in the Black Swan photograph. So the effects of towering cause this heliport to be stretched up about 0.03 degrees in angular size. And this supported our position that the horizon could also appear higher. But again, the flat Earth community claimed that this was absolutely impossible. But they want us to consider that maybe downward refraction of over 26 degrees is possible. Now, flat earthers also seem to forget that not only is celestial navigation a real science, but it was actually used for hundreds of years before the advent of GPS. Now, this is just one example of celestial navigation that you can find with a Google search, and they all include corrections that need to be made for a sighting, and of course those corrections include atmospheric refraction. And how you do it is by using this table shown over here on the right. Now the center column is for stars and planets, and if you look at the left side of it over here, this would be the apparent altitude or the observation that you actually make, and then over here would be the correction to show you where the actual altitude was. So let's say if you made an observation and it was between 9 degrees 56 minutes and 10 degrees 8 minutes, then you would subtract 5.3 minutes off of that observation to get the correct altitude. So what I want to do is show what realistic refraction rates would be for 10, 20, 30, and 40 degrees above the horizon. So first I went through the chart and found the correct area that corresponded to these degrees. And then I changed all of these corrections that are in minutes into degrees so it's easier to understand. Now, according to celestial navigation tables, these would be the apparent positions of Polaris above the horizon due to atmospheric refraction for these latitudes. Now, it did not include a figure for 0 degrees or at the equator, but that is typically stated as a half a degree. And of course, when you subtract out the correction from the apparent altitude, you get the actual altitude of Polaris for each one of these latitudes. And notice that it is actually a little bit lower than the apparent altitude. Now, this is a comparison of the apparent altitude of Polaris at each of these latitudes that you would expect to see with the calculated altitudes for a flat Earth. Now, are flat earthers really going to make the claim that these are legitimate rates of refraction? Especially when these are the actual corrections for atmospheric refraction used by celestial navigators? Well, if that's the case, I think you would have to agree with me that's not refraction, but that is Flerfraction. So the next time a flat earther tells you that sextants only work on a flat Earth, tell them to prove their point and use those triangles to calculate the altitudes of the Sun and Polaris. Of course, don't hold your breath waiting for an answer because their understanding of celestial navigation is just another flat Earth fairy tale.